Engineers working in Python rely heavily on SciPy.optimize.curveFit. You pass it a model and some data, and it hands back the parameters. Because it requires so little setup, it is frequently treated as an opaque box that simply guesses the right answer. But curveFit is not an independent solver. It is a translation layer. Its function is to convert your user-defined model into a standardized mathematical format so that lower-level min-pack optimization algorithms can read it. Those underlying algorithms do not evaluate the overall geometric curve of your data. They have a single, extremely narrow metric for success. Look at this technical schematic. The system only registers the vertical distance between the data points and the fitted segment. These vertical mismatches are the residuals. The entire engine is built around a single mandate: calculate those specific vertical distances and drive them to zero. To achieve this, the input data flows through a strict four-step computational pipeline. This diagram maps the process. The user's model function is wrapped into a residual function, passed to a least squares optimizer, and finally extracted as the optimized parameter and covariance arrays. By tracing the mathematical logic at each step of this pipeline, we can observe exactly how the engine navigates parameter space, why certain fits fail silently, and what the resulting covariance matrix actually measures. The critical work begins in the second stage of the pipeline, where the wrapped function computes the objective. This equation defines the objective function. The system minimizes the total sum of squared errors. Squaring these residuals is a deliberate choice. It heavily penalizes large deviations, prevents positive and negative errors from canceling out, and ensures the problem remains differentiable. The sigma argument scales measurement uncertainty before squaring. By default, SciPy treats every point equally, but providing a one-dimensional array of standard deviations ensures points with larger uncertainty receive less weight, influencing the final fit far less. The optimization engine will relentlessly adjust parameters in order to shrink this newly scaled sum of squared errors. However, because the user's model is typically nonlinear, the optimizer lacks a direct algebraic formula to calculate the absolute minimum in one step. Without a closed-form solution, the optimizer faces a distinct computational dilemma. It has to iterate, making calculated jumps across the parameter space. This graph illustrates the core trick. Near the current parameter estimate, the algorithm pretends your nonlinear model is linear, creating a local tangent. Because this approximation is only valid for short distances, the engine takes a short step, stops, and recalculates. To calculate that precise tangent, the system relies on the Jacobian matrix. Think of it as the mathematical measure of model sensitivity. As shown, each column tells the optimizer precisely how individual residuals react if it nudges exactly one parameter. If you do not explicitly provide a mathematical derivative for the Jacobian, SciPy estimates these sensitivities numerically. This numerical estimation calculates the model multiple times per step, taxing the system's computational resources. The Jacobian serves as the deterministic steering mechanism for the solver. Calculating it accurately and efficiently is the primary bottleneck of nonlinear optimization. Once the Jacobian is mapped, curveFit uses algorithms to choose step size. The default Levenberg-Marquardt algorithm acts like an automatic transmission, continuously asking, how much should I trust my local linear approximation? It controls this trust using the damping parameter lambda. Small lambda uses Gauss-Newton for fast, aggressive steps. If the approximation fails, it increases lambda, shifting into a cautious, robust gradient descent. Levenberg-Marquardt operates efficiently until you introduce parameter constraints. If you apply hard mathematical bounds, it breaks down. The wrapper automatically switches to the trust region reflective method, constructing strict, localized subproblems to keep steps inside viable boundaries. These optimization algorithms act as highly structured mathematical rule sets. They govern how far the engine travels along the tangent before stopping to remap the territory. When the optimization engine finally converges, it returns two arrays. This dashboard breaks down the output. The popt vector contains the exact best fit parameter values that minimize the squared residuals. The second output, pcov, is the covariance matrix. The formula at the bottom details the reality of this matrix. It is an approximate curvature matrix derived directly from the inverse of the Jacobian. The grid layout is straightforward. The diagonal values represent the estimated variances, or standard errors, for each parameter, while the off-diagonals track correlations, showing if parameters mathematically depend on one another. Interpreting this matrix requires navigating a specific mathematical trap regarding the absolute sigma argument. This logic tree outlines the two distinct behaviors. By default, absolute sigma is set to false. The engine assumes your input sigmas are only relative weights. It then applies the rescaling math shown on the right, using the variance of the final residuals to estimate the overall scale of the noise. Setting absolute sigma to true bypasses this rescaling entirely. It forces the covariance matrix to treat your provided sigmas as absolute true measurement uncertainties. If you leave this parameter at its default setting while expecting absolute error calculations, the standard errors returned by curve fit will be relative, potentially leading to wildly misleading confidence intervals. Because the entire engine calculates steps by moving strictly downhill along local linear tangents, it remains structurally blind to the broader mathematical landscape. This topographic visualization highlights the first major consequence, local optimization. If you provide a poor initial guess, the P0 argument, the algorithm will simply roll down into the nearest local valley, completely missing the true global minimum. The second major limitation is parameter scaling. The text box on the right explains that attempting to fit parameters separated by multiple orders of magnitude destroys the engine's ability to select a functional step size. A step that is perfect for a parameter scaled to 10 to the 8th is catastrophically huge for a parameter scaled to 10 to the -6th. Providing an accurate initial guess, manually normalizing your parameters, and supplying an exact Jacobian function are not merely optional optimizations. They are strict mathematical prerequisites for the solver to function accurately. Curve fit acts as an incredibly efficient bridge between user models and deep mathematical solvers. But if you feed it unscaled data and poor initial guesses, it will relentlessly optimize a bad approximation. Producing rigorous results requires an engineer who understands the precise mechanics turning beneath the wrapper.